this is the fifth and final lecture of week 3. In this week, we have introduced the concept of convergence in probability for a sequence of random variables defined on some probability space. This third mode that we have considered, we have also compared it with earlier two modes of convergence, which are almost sure convergence and convergence in LP. And we have seen that this third mode of convergence, which is the convergence in probability, is implied by this other earlier two modes of convergence. We have also seen some equivalent formulations or equivalent conditions for convergence in probability. Finally, we have also talked about some other additional properties of these modes of convergence. In this lecture, we are going to discuss some specific problems related to the material that we have covered in week 3. Without further delay, let us continue the discussion with the slides. So, we are going with this same notation scheme that omega f p denotes a probability space, and if required we will specify some explicit probability spaces for concrete examples. But always we will take omega f p to be a probability space, and the sequences of random variables that we considered will be assumed to be defined on this probability space. So, let us look at some problems based on the content of week 3. Recall that we have seen this condition equivalent to the convergence in probability, that x n, a sequence of random variables, converge in probability to a random variable x if and only if this quantity, which is the expectation of x n minus x modulus minimum with 1, that quantity goes to 0 as n goes to infinity. Now, we have already discussed some examples of convergence in probability, and these examples essentially were through the convergence that we have established earlier, either for the almost sure convergence or some LP convergence. Now, what we do is that we go back to these examples once more and verify that this equivalent condition that we have recalled here also is true. So, this will justify in explicit examples that the corresponding equivalent condition for convergence in probability is true. So, let us recall the examples. So, in example 1, we had considered this very specific probability space where omega was taken to be the interval 0 to 1, and on top of that we had considered the sigma field, which is the Borel sigma field on 0 to 1, and finally, the corresponding measure was taken as the restriction of the Lebesgue measure on this sigma field. Now, if we look at that specific probability measure, when we look at the specific restriction of lambda to this sigma field, we will end up with a probability measure which we denote by p. Now, here we end up with therefore probability space omega f p. So, on top of this we considered these explicit random variables given by this, that for n from 1, 2 and so on, n all positive integers, we consider first of all omega in the interval 0 to 1 by n, and there we set the value r to the power n, where r is chosen to be some real number greater than 1. Otherwise, if omega is outside this given interval 0 to 1 by n, then we will consider the value 0. So, that is how the corresponding sequence of random variables was constructed. Now, in this case what we have is that the probability of the event where modulus of x n takes value strictly less than 1, that turns out to be exactly the event when x n takes the value 0. Note that as long as we are considering two possible values of x n, so one value is r to the power n, the other is 0, but as long as r is greater than 1, r to the power n is also greater than 1. So, therefore, if we only restrict ourselves to the values of x n being less than 1 or modulus of x n being less than 1, in either case we end up with the exactly the event that x n is taking the value 0. and xn takes the value 0 on this set of omega, where omega is greater than 1 by n and less or equal to 1. So, that is why this interval comes in, and the corresponding measure, as we understand it, it is actually the Lebesgue measure. So, therefore, we have explicitly computed the probability when modulus of x n is less than 1, and that turns out to be 1 by n. So, therefore, we can actually write that modulus of x n minimum with 1, that quantity essentially appears with the value 1, because the value of the random variable here is greater than 1, which is r to the power n. But if we consider minimum with 1, then this must be 1. So, therefore, on this range the value is 1. On the other part of it, we have already identified that it must be omega belonging to open 1 by n to closed 1, and there the value is exactly 0, because here the values of x n is exactly 0. So, therefore, we have split our domain, which is 0 to 1, into two disjoint parts. So, on one part this x n minimum 1 takes the value 1, and on the other part it takes the value 0. So, therefore, we can now explicitly compute corresponding expectation, and this is just 1 by n, and as n goes to infinity, this goes to 0, and therefore, this validates that we must have convergence in probability for the sequence x n, and here it is also immediate that the limit turns out to be 0. All right. So, let us look at another example which we have seen earlier. So, again we continue with the same probability space, meaning omega is taken to be the interval 0 to 1. We look at the corresponding Borel sigma field, and we also restrict the Lebesgue measure on 0 to 1 on this sigma field, and therefore, we end up with this probability space. Now, here we considered in example 2 a triangular array of random variables. So, here first of all n varies over all positive integers, and corresponding to n we also look at this possible range for the numbers m. So, m is again some integer between 1 and n. So, for such a triangular array, which is defined in this way that it is taking 0 or 1 value, and therefore, it is of the structure of a indicator. So, it is an indicator of this type of an interval that we considered on our set, which is exactly equal to 0 1 interval. All right. So, here again we can try to make an estimate for the term of interest. So, we want to show that this sequence of random variables goes to 0 in probability, in the sense of convergence in probability. So, here what is happening is that first of all we observe that the random variables modulus of x n m minimum with 1 is of course less or equal to modulus of x n m. So, therefore, the corresponding expectations will also satisfy the same inequality. Now, remember this expectation that we have here, this is nothing but the L 1 norm of the corresponding random variable x n m. Now, here we recall that the L 1 norm is dominated by the L p norm, and the L p norm is nothing but the pth root of the pth absolute moment of the random variable x n m. So, therefore, what we end up with is that our term of interest is dominated from above by the corresponding L p norm. So, here p is chosen to be any number between 1 and infinity. Now, here what we recall is that we had explicitly computed this L p norm earlier when we discussed example 2, and there we have computed the value to be exactly this quantity, that it is the pth root of 1 by n, and as n goes to infinity, this quantity goes to 0, and this was used earlier to show that the sequence x n m goes to 0 in the L p space. Now, here since we are comparing with the convergence in probability, first of all the convergence in the L p space implies the convergence in probability in this setting, and we are trying to verify the corresponding equivalent condition, and here what we have is that by the means of these estimates that we have derived, the corresponding term also goes to 0. So, therefore, this left hand side quantity goes to 0 as n goes to infinity. All right. So, now with these two specific examples, we can now convince ourselves that this looks justified, that we can look at the corresponding bounded random variables given by mod x minimum 1 when we are dealing with convergence in probability for some random variables x. All right. So, now let us consider another interesting property involving the L1 and LP convergences. So, this fact, it says that convergence in L1 does not imply the convergence in L2. So, we are going to talk about a sequence of random variables which converge in the sense of L1 convergence, does not converge in the setting of L2 space. So, let us see. So, here what we do is that we start with some explicit random variable x, we will choose such a random variable x on some probability space with some certain property. So, the property that we ask is this, that its first absolute moment should be finite. So, that in particular will imply that expected value of x is a real number. Now, we also will look at the corresponding second moment, but we assume that such a random variable we are considering that the second moment turns out to be infinity. So, in this case what we happen to choose is that this random variable should be in L1, but not in L2. Now, here what we can look at is that we can choose our x to be also non-negative. How? Because if x itself is not non-negative, then we will simply look at y equals to mod of x. Now, then note that expected value of y, which is also the same as expected value of mod of y, y is now non-negative. This turns out to be exactly the expected value of mod of x, which we assume to be finite, and expected value of y square is exactly expected value of x square, which turns out to be infinity as per our assumption. So, therefore, without loss of generality, we can assume that our x is actually non-negative. If x is not non-negative, then we will just look at the mod of x and it will also satisfy the corresponding property. All right. So, let us take such a random variable x which is non-negative, which has finite first absolute moment, but the second moment is not finite. Now, what we do is that we look at certain truncated random variables. So, here these truncated random variables is going to give us a sequence which we denote by x n. So, for any positive integer n, what we do is that we look at the set of points where x takes the value less or equal to n. Remember, x always takes value greater or equal to 0 with full probability. So, we are just restricting ourselves to the situation when x is taking values between 0 and n. So, on such a set we will take the value x. So, that is how this is defined. Otherwise, this indicator will turn out to be 0 and therefore, the value turns out to be 0. All right. So, that is how we end up with a sequence of random variables. Now, let us look at the structural properties of this sequence of random variables. So, with probability 1, the random variables x n is taking values between 0 and n, this is by definition, and therefore, the nth random variable x n is always bounded, and therefore, it will give you that it must be in L p for all p. So, it has all orders absolute moments. All right. So, let us look at these x n's in the specific case of L 1 and L 2. So, here not in L 2. So, that we have assumed, but x n is in L 2. Therefore, we immediately will conclude that x n cannot converge to x in the L 2 space setting, because the limit random variable that we are asking for, the x, which is not in L 2. So, therefore, the L 2 convergence does not hold in this setting. However, we want to look at the corresponding L 1 convergence. So, let us see. So, we already have that x n's actually increase to x. Why this is so? So, let us go back to the definition. So, when my n increases, for every fixed omega, I will end up with a number small n whenever this x of omega will turn out to be less equals to n. So, if we look at a fixed value of omega and let n go to infinity, then after a certain stage onwards this inequality will start be getting true, and therefore, x n will match with x, and therefore, x n will converge to x. So, here we also note that by our definition x n's are actually increasing in n. So, this can be immediately verified from the setting. So, therefore, we have this pointwise limiting operation as n goes to infinity, and x n's are all non-negative and increases to x. So, we can appeal to the monotone convergence theorem and claim that the integrations which give us the corresponding expectations converge to the expected value of x, which we now have assumed to be finite. So, remember all the random variables that we are considering here are taking non-negative values. So, here we immediately also will conclude that expected value of modulus of x minus x n. Now, here x n is always less equals to x. So, this modulus value is simply the difference x minus x n, and therefore, this quantity goes to 0 by our understanding as n goes to infinity. So, therefore, x n's converge to x in the L 1 space. So, we have a explicit sequence of random variables which converges in L 1, but not in L 2. So, now we also note in particular that the x n squared they also increase and increase to the random variable x squared, and all these random variables are non-negative. So, again we can appeal to the monotone convergence theorem and say that the limit of the corresponding expectations must be the limit of the expected x squared, which is assumed to be infinity in this case. So, this observation will also be interesting, and we will come back to this observation in a later lecture. So, we have a explicit sequence which shows that the sequence converges in the L 1 setting, but it does not converge in the L 2 setting. Okay. So, let us look at some properties involving infinite measures now. So, in this week we have been focusing on the convergence with the underlying measure being a probability measure and the corresponding measurable functions being random variables. So, that is our main focus that will be throughout the course. However, we can also ask how the things may differ if we consider a infinite measure and consider sequences of measurable functions. So, we give some examples showing that many of the results that we derive for probability measures or more generally for finite measures may not hold if we deal with an infinite measure. So, let us see some interesting statements. So, we start with the again the Lebesgue measure on the real line. So, this is an infinite measure. So, what we show is that the convergence in L infinity does not imply the convergence in L p. So, here remember if you are dealing with a probability measure, then L infinity convergence implies L p convergence. So, let us look at some explicit sequence of measurable functions in order to establish this example. So, what we do is that on 0 to 2 to power n, we look at the value 1 by n, otherwise we will set the value 0. So, this is giving us some nice measurable functions. Now, let us look at the corresponding L infinity norm of the functions f n. So, here it turns out to be 1 by n exactly. So, that is the supremum quantity, and therefore, this goes to 0 as n goes to infinity. So, therefore, we have the L infinity convergence in this setting. However, if we now choose to look at the L 1 norm of this sequence of functions, this is nothing but the integration of mod of f n with respect to the Lebesgue measure. Now, here the functions take the value 1 by n on the interval 0 to 2 power n, and therefore, we can immediately compute the value of the integration to be 2 power n divided by n. However, as n goes to infinity, this quantity goes to infinity, and therefore, the sequence f n does not converge in the L 1 space, okay, because the corresponding L 1 norms are in fact are going to infinity as n goes to infinity. So, we can in fact do a similar computation for other L p norms when p is between 1 and infinity. So, what this shows is that if you are dealing with an infinite measure, in that setting the L infinity convergence need not imply the L p convergence, where p is between 1 and infinity. infinity excluded. We also now look at another interesting property involving these infinite measures, which is the Lebesgue measure. So, we remember that this Lebesgue measure is actually translation invariant in this sense that if we look at any Borel set capital A and shift it by some real number small x. So, this simply gives you this set of numbers, then A plus x turns out to be a Borel set and we can ask about the Lebesgue measure of this new Borel set, and it so happens that it can be shown that the Lebesgue measure is the same with the original set capital A. And here this is what we mean by the translation invariance of the Lebesgue measure. Now, if we look at any measurable function on the real line, as a consequence of this translation invariance, we immediately end up with this observation that the integration of f with respect to the Lebesgue measure is again does not get affected by the shift in the origin. So, that is how we will observe it, and therefore, this property actually extends to certain nice properties of all these LP spaces. If we look at these functions in this LP setting where p is between 1 and infinity, infinity excluded, then what we end up with is that this integration is exactly the integration of mod f to the power p, and this is true for any x. So, what we are observing is that if we take any LP function, we can translate it and get another LP function, all right. So, therefore, the LP space again in this sense remains translation invariant. So, finally, we go and discuss some interesting example of an almost sure convergence. So, we start with a specific random variable with the distribution being uniform on 0 to pi by 2. So, here using this x, we will construct a sequence which we denote by x n in this way that we are going to consider sine of n x. So, for each positive integer n, this is going to give us this random variable x n. Now, let us look at this observation that sine of x takes the value 0 only when x takes the value m times pi for some integer m, all right. But then as x takes the uniform distribution on 0 to pi by 2, therefore, these explicit discrete values will end up with probability 0. Now, let us do this manipulation involving this kind of an sample average for the corresponding sequence that we are considering now. So, here what we do is that x n is sine of n x. So, that is what we are considering. So, let us divide and multiply by sine x in this setting. So, we will end up with this kind of a summation here, and we will also have to divide by n that was already there in the original expression. Now, here we use this trigonometric identity that this sine times sine that can be written in terms of a difference like this with divided by 2 here. So, this is a minor correction that will be made in the final lecture notes, all right. So, now once we have that, then what we end up having is that this quantity inside the summation that will actually collapse. You see that if we consider j equal to 1, then we are looking at cos of 0 x minus cos of 2 x, but then for j equal to 3, if we consider the same number, we will end up with cos of 2 x minus cos of 4 x. So, therefore, this cos 2 x cancels off from the expressions. Again, if we consider all even values of j, then again we can establish similar cancellations. So, at the end of the day, the number of terms here will collapse, and we can ensure that this summation that we observe from j equal to 1 to n, that will collapse and that will turn out to be some combination of cosine functions, and that will remain bounded. Therefore, since the cosine function is bounded and all the rest of the quantities remain bounded, then these quantities go to 0 as n goes to infinity, and this happens almost surely with full probability, all right. Now, here what is happening is that we have divided by sine of x, but we have also justified that random variable sin x takes the value 0 with probability 0. So, therefore, the division is also well defined. So, there is no loss of any generality in these calculations, and therefore, we have obtained a nice interesting observation which shows that these kind of averages actually go to 0 almost surely. So, we have discussed in this lecture some nice examples involving the content that we have covered in the week 3. In particular, we have compared convergence in probability with other modes of convergence, and we have seen equivalent conditions for convergence in probability. In the next week's discussions, we are going to look at further properties of this type of convergences, and we are also going to consider such kind of averages, sample averages involving random variables. So, we will discuss that in the next week lectures. We stop here. Thank you.